working in plasmonics. Jen was a graduate student of Harry Atwater, who was my advisor's advisor. And after graduating from Caltech, she joined Paul Alivisatos' group at Berkeley and learned a little bit about how to synthesize various nanoparticle assemblies in order to be able to make the kinds of plasmonic and metamaterial structures that she's had so many high-impact papers describing their optical response. Just a few honorifics. She's been at Stanford for just under 3 years and has already won an NSF Career Award, the Air Force's Young Investigator Program, and was named by MIT's Technology Review as one of 35 influential investigators under the age of 35. So it's my pleasure to announce Jen. Thank you for coming.
Cool. Well, thanks, John, for the introduction and for the invitation to speak as part of this seminar series. It's so much fun to be back at Santa Barbara. When I was a graduate student at Caltech, my boyfriend, now husband, was a PhD student in electrical engineering. So I got to come to Santa Barbara almost every weekend and always kind of viewed it as a little bit of paradise. Even when the weather is a bit more dismal, it's still such a fantastic place to be. And there's obviously really great research happening here. So thank you for taking many of your mornings and early afternoons to share your work with me. And thanks for those of you who haven't met yet for coming out this afternoon to my talk. So like John said, I'm an assistant professor in the Material Science and Engineering Department at Stanford University. I've been there about 3 years. A lot of our work has been kind of in, I guess, more like fundamental plasmonics work and also some applications to optical trapping. I'm kind of a rookie or a newcomer to the energy sector, energy applications of plasmonics. So many of the ideas I'll be presenting today are rather new, but hopefully we can have like some good discussion after the talk. I'd like to acknowledge, of course, the graduate students and postdocs who did most of the hard work to make this work possible. In particular, John Scholl, Andrea Baldi, Ashwin Atre, Dionne Wu, Justin Briggs, Michael Wisser, and Itzel Garcia. Eileen Coe is a staff scientist. She keeps our aberration-corrected TEM up and running and in tip-top shape. So we've been starting to do a lot of really nice environmental TEM measurements. And then I'd also like to acknowledge collaborations with some of my colleagues, Alberto Soleo and Mike McGeehee. So since I said I'm kind of a rookie to the energy sector, my title has the kind of classic non-descriptive flair, progress and challenges in plasmon-enhanced photovoltaics and photovoltaics and photocatalysis. Probably a better title for my talk would be Oh, the Places Plasmons Go, because we're going to focus a lot today on surface plasmons and what sort of opportunities can be enabled by using the properties of small metallic nanoparticles in energy-related challenges. So you may notice that my title has a bit of a Dr. Seuss flair to it. So that's the outline for my talk that I'll present, a poem. Oh, the plasmons go quantum when particles are small. Their spectra shift blue. Their peaks are less tall. So in the first part of my talk, I'll show you how we've been able to probe the plasmon resonances of extremely small particles ranging down to about 1.5 nanometers in diameter. And when you get to such small sizes, plasmons as collective oscillations of conduction electrons experience the effects of quantum confinement. All right. And because they're sensitive to their surroundings and charge, catalytic sensing is easy on particles small and large. We'll coat titania over a metallic core. Ultraviolet light gets absorbed. Electron-hole pairs separate more. So kind of a goal is to use these small particles, which are very catalytically active, to sense multi-electron redox reactions kind of with very high spatial, spectral, and ultimately time resolution. And as a step towards that goal, we're going to look at titania-based catalysis, where we'll take, in this case, a medium-sized silver nanoparticle, coat it with titania, shine ultraviolet light on it, and then I'll show you how we can probe shifts in the plasmon resonance as electrons get transferred onto and off of the silver core. Okay, lastly, solar photons span wavelengths red, green, and blue. For efficient photovoltaics, we'll use upconversion too. In the last part of my talk, I'll show you how we can use 2-photon processes to basically collect some of the photons that would get transmitted through a photovoltaic cell or a photocatalytic cell and combine those photons together into a higher energy photon that then can be used by the cell above it. Okay, so I guess many of you come from different backgrounds, and I wasn't sure how familiar this audience was with plasmons. I know some of you have been in the field for over 30 or so years, but for those of you who are newcomers, I thought I'd just start with a basic primer on the plasmon resonances of conducting nanoparticles. So let's take a conducting particle, and when light is incident on this particle, generally the electric field of light is going to drive the conduction electrons up or down in response to this electric field. So as light oscillates, so do the conduction electrons in this conducting nanoparticle. It can be either a small metallic particle or a highly doped semiconductor. And assuming the particle is much smaller than the wavelength of light, as is the case for most catalytically active nanoparticles, then we can write the polarizability, or how easy it is to move those conduction electrons, in terms of the size of the metal particle. So here R is the radius. Also in terms of the permittivity of the particle, epsilon, and in terms of the permittivity of the surrounding medium, epsilon m. And then given a certain polarizability for the particle, we can write the absorption cross-section and the scattering cross-section in terms of the polarizability. So basically these formulas are telling us how large the particle looks compared to its physical size to incident electromagnetic fields. So basically a small metallic particle can have an absorption cross-section that can be many times larger than its physical cross-section whenever the polarizability is maximized. As an example of that, let's consider a particle composed of silver, and if it's in vacuum, you'll notice that the polarizability is maximized when the denominator basically becomes very small, which of course we can achieve when epsilon of silver is equal to -2, assuming our particle is in vacuum, where epsilon of the medium is equal to +1. So you'll notice that the dielectric function of silver is equal to -2 at a wavelength of 355 nanometers. There's, of course, a small imaginary component to the permittivity as well. But at this frequency, you get a very strong peak in your absorption efficiency of the particle because the polarizability is maximized. Now, one of the advantages of plasmonic particles is that you can tune their plasmon resonance based upon things like their size, also their aspect ratio. So if you slightly squish the particle in one direction so it's slightly ellipsoidal, you get a redshift in the surface plasmon resonance. Plasmon resonances are also highly sensitive to the permittivity of the surrounding medium. So if instead of having the particle in vacuum, if it's in water, we again get a shift of the surface plasmon resonance. And plasmons are also sensitive to the number of conduction electrons in the particle. So if here we take a 5 nanometer particle and we start adding more electrons onto it, then we get a successive blue shift, with that blue shift increasing with the number of electrons that are added onto the particle. So if you look through the literature in the past decade, surface plasmon resonances have been used for quite a few energy-relevant processes, say to enhance photovoltaics or to enhance photocatalysis. And this is just a small cross-section of the papers that are out there in the literature. But as an example, people have used the large absorption cross-sections basically to enhance the amount of photocurrent that's produced in a photocatalytic cell. So here's an example from one of my colleagues, Mark Brangersma, and his postdoc, Isabel Tommen, who now is a professor at Rice University. And in this paper, they used small metallic particles, here composed of gold, that were embedded in iron oxide. And when they were illuminated on resonance, here the plasmon resonance of gold was right around 600 nanometers, they not only got a large absorption enhancement, but they also got a pretty significant enhancement in the overall photocurrent that was generated in their iron oxide catalyst. So they were able to use this photocurrent enhancement to enhance the efficiency ultimately of overall water splitting using iron oxide as the catalyst. A second, I think, really encouraging area of research in plasmonics is to use hot electrons to enable very high energy conversion. So one of the cool things about surface plasmon resonances is that plasmons are going to basically decay. But as they're decaying, some of the energy of the electrons is slightly above the Fermi energy. And provided you have the right sort of contact formed between, say, a metallic nanoantenna and a semiconductor, some of these hot electrons formed by plasmons as they're decaying can basically either transport over the Schottky barrier or tunnel through a Schottky barrier between a metal and a semiconductor. So recently, Naomi Hollis used this hot electron transport to enhance photocurrent in a silicon-based photodetector. Silicon normally is limited to detecting photons that have an energy higher than the band gap. The neat thing about this device is that she was able to extend the range of photosensitivity to photons that had energies equal to the Schottky barrier height. So basically, she could detect photons that were farther out into the near infrared than photons that were just at the band gap of silicon. I'd also like to draw your attention to some very nice work that was just published in Nature Nanotechnology by one of your colleagues here at UC Santa Barbara, Martin Moskowitz, where he was able to use hot electrons in a gold nanowire also to enhance or to enable overall water splitting. A few other applications of surface plasmons in the energy sector is, I guess, as reaction sensors of catalysis. Here's a paper from the Alivasados group where they had a gold nanoparticle surrounded by a palladium shell. And when palladium absorbs hydrogen, you basically change the refractive index of the shell, and that causes a shift in the surface plasmon resonance. That's quite a few nanometers. So you can get some information about the kinetics and thermodynamics of hydrogen loading in a palladium shell by using the shift in plasmon resonance of this composite core shell particle. As one final example, the Mulvaney group in Australia was able to probe redox reactions using gold nanoparticles that were embedded in a solution that donated electrons to the gold particle. So here, as a function of reaction time, you'll notice the peak wavelength shifted from about 620 nanometers all the way down to 600 nanometers, corresponding to transport of about 800,000 electrons, or transfer of about 800,000 electrons onto the gold nanoparticle. So I think, like I said, this is just a small cross-section of the work that's going on in the field of plasmon-enhanced, I guess, energy conversion processes. But I think overall the message is that there's a lot of hope for using conducting nanostructures to both enhance photoconversion and to sense redox reactions. But if you look at each of these, I guess, applications, you'll notice that the scale bar is quite large, typically on the order of tens to hundreds of nanometers. And yet, if we're interested in photocatalytic reactions, the size of most particles that are actually catalytically active is considerably smaller. This is a plot from Jens Norskov at Stanford and SLAC, where he plotted the catalytic activity of gold nanoparticles as a function of their size. So keep in mind, on the last slide, I showed you that surface plasmons can enable enhanced catalysis, but that was generally using larger nanoparticles. If we really want to sense catalytic reactions using, say, surface plasmon resonances, then we're going to need to look predominantly at particles that are smaller than about 5 nanometers, where their catalytic activity significantly increases. So in the first part of my talk, I guess I want to address the question, can we detect plasmons from particles in the sub-10 nanometer regime, given that ultimately one of my goals in my group is to be able to use surface plasmon resonances to directly probe redox reactions. So I guess that brings us to the second part of my question. Can we use plasmons to monitor photocatalytic reactions in situ? So we're going to look at silver particles surrounded by a titania shell, and I'll show you that using optical microscopy, we have some preliminary results showing that we can detect shifts in the plasmon resonance upon charging of the silver particle, and ultimately we'll combine some of these optical measurements with some of these measurements on extremely small metallic particles. Okay, then, like my Dr. Seuss poem alluded to in the final part of my talk, I'll address the question, can we improve below band gap absorption of solar photons for photocatalysis and photovoltaics? So most photocatalytic materials only absorb light efficiently, maybe up through visible frequencies. So there's a huge portion of the solar spectrum that basically goes to waste. So can we use upconversion and combine that with plasmonic systems to get very high efficiency two photon processes? Okay, so starting with this first question, can we detect plasmons from particles in the sub-10 nanometer regime where we have a high degree of catalytic activity? Okay, so a bit of history. Why is this so challenging to begin with? Like, why has a field of plasmonics generally focused on slightly larger particles? I realize it's kind of an oxymoron to say 20 nanometer nanoparticle is huge, but I think we're in the regime now where, I don't know, maybe quantum will be the new nano at some point. Okay, so probing the plasmonic properties of such small particles is challenging for a number of reasons. First of all, when particles are so small, they scatter light very weakly. So if you just want to use an optical measurement to detect plasmon resonances, generally you can go in the lab and easily whip up a batch, say, of 30 nanometer gold nanoparticles, and you'll easily see the scattering from that solution as, say, like a red fluid or a red color. But then as you make the particles smaller and smaller, they scatter much more weakly, and your solution looks a lot more transparent. So when you get to such small sizes, generally absorption tends to dominate a bit more over scattering, and that makes doing optical measurements a bit more challenging. So what people have done to get around the weak optical scattering is just say, well, I'll make a lot more particles. That way, you know, I can just kind of sum up the cumulative scattering effect. And you can do that, but then you suffer from particle heterogeneity. If you wanted to look at an actual catalytically active particle, say you're in the 1 to 2 to 3 nanometer regime. So you're already dealing with small particles, so just a small degree of heterogeneity is really going to broaden out your plasmon resonance. So you're not going to know, like, is my plasmon resonance broad because plasmon resonances of small particles are inherently broad, or is it because I just have a very low degree of monodispersity in my sample, right? If you have a broad distribution of particle sizes, that's also going to broaden out your signal. Another factor that's made these sorts of measurements challenging is organic ligands. So when you colloidally synthesize nanoparticles, generally you're going to use ligands that will stabilize your particle during the synthesis. So basically you have a layer of soap around your nanoparticles, and that also kind of tends to damp out your surface plasmon resonances a little bit. So if we really want to look at small catalytically active particles that also have plasmon resonances, we somehow need to get around each of these problems. Just to give you a flavor for some work that has been done in the past, this is an ensemble measurement of silver nanoparticles that were kept with oleolamine. And Peng and Schatz and colleagues looked at the absorption cross-section as a function of wavelength as the particle size was reduced from 17.8 nanometers down to 2.2 nanometers. And you'll notice that the signal decreases pretty quickly as you get to small particles. In fact, just to get the 2 nanometer particles on the same scale, they had to multiply the absorption cross-section by about 400. So the signal drops off pretty quickly, even in ensemble measurements. And here they noticed a small redshift of the surface plasmon resonance on the order of like 0.03 electron volts. So looking at smaller particle plasmon resonances, on the one hand, indicates a redshift. There are, however, many other experiments that indicate a blue shift. So here's a single particle measurement from the Sandogar group where they looked at scattering of about 60 nanometer nanoparticles using a confocal heterodyne technique, so an optical measurement. And then as the particle size was reduced to 10 nanometers and 5 nanometers, they started looking at absorption, which is why now you see this dip in the intensity that they were looking at. And they noticed a blue shift on the order of about like 0.05 or so electron volts, which is what you might expect if your particle is becoming smaller and you're entering a regime where quantum effects may be playing more of a role. One of the challenges, however, with this optical measurement is they couldn't directly correlate the size of the particle to its plasmon resonance. So they knew that this particle was 60 nanometers plus or minus 12 nanometers. They knew, for example, this particle was 5.4 nanometers plus or minus 0.8 nanometers. So ideally, we want to do a single particle measurement where we can correlate the particle spectra with the particle geometry. So in our group, we turned to electron energy loss spectroscopy. So I don't know if you have an aberration-corrected TEM on campus with EELS capabilities. If not, our TEM is a user facility, so I encourage you to contact me if you're interested in this technique. What you do is you take a very focused electron beam, a scanning transmission electron beam, and you pass it through your sample of nanoparticles, which can be placed on any thin substrate. We did our experiments both on carbon. We've also done them on silicon and silicon nitride, silicon dioxide, pretty much anything that's transparent to electrons. And then when your electron beam passes through your nanoparticle sample, basically the electrons are going to lose some energy corresponding to the modes or the surface plasmons that get excited in your particle. So you'll take the transmitted electron beam, pass it through an EELS spectrometer and onto a CCD, and basically measure the energy loss of the electron beam after it's passed through your sample. And that's an indication of what modes were excited in your nanoparticle sample. So an advantage of scanning transmission electron microscopy, which is how we do all of our EELS, or electron energy loss measurements, is that we have an imaging spatial resolution of about 0.25 nanometers. If we're operating our TEM in wide area TEM mode, so we just have our electron beam over a larger area, we have an imaging spatial resolution of 0.07 nanometers. So we can swap between spectroscopy mode and high resolution TEM mode to know what is the plasmonic spectra of our particles, and then what is the exact shape and size of our particles. And I won't be able to talk too much about some of the catalytic work we're doing in this presentation, but our TEM also has environmental capabilities. So we can flow in different gases, and we can also do these sorts of measurements in liquid cells. So what I'll be showing you in the next 10 or so minutes are the results that are kind of the control experiment for a lot of the catalytic measurements we're going to be doing in the near term. Okay, so I mentioned that another factor that's made kind of understanding plasmon resonances of small particles challenging is the effect of long, bulky carbon ligands on the surface of particles. So we synthesize particles without organic ligands, both to minimize the effect of surface damping, and then also to minimize the effects of organic contamination. So if you have the electron beam interacting with a long carbon chain, generally that'll undergo hydrocarbon cracking and contaminate your sample with soot. So if you do try to do this measurement, make sure you get rid of organic ligands. Here are some of our particles, ranging from about, I guess this is a 10 nanometer nanoparticle. We made nanoparticles up to about 20 nanometers. And then you can see the size of the particle being reduced. The smallest particle we probed was 1.7 nanometers in diameter. And these are silver nanoparticles, so they have a very large polarizability, kind of increasing our signal-to-noise ratio. Okay, so then we can switch to STEM mode. Like I mentioned, in STEM mode, we have slightly poorer spatial resolution. But we come in with our electron beam just at the edge of the nanoparticle. We detect the energy loss, and you notice just one strong peak, just a little bit redshifted from 3.5 electron volts. This corresponds to the surface plasmon resonance. So basically, the electron beam comes in. It's kind of a point negative charge, which means that in the particle, you basically induce a point positive charge here, a negative charge over here. So you have a strong dipole moment in this direction, causing those conduction electrons to oscillate. Then when you move over to the center of the particle, now you get a second peak. This corresponds to the bulk resonance. So the electron is passing through more of the volume of your nanoparticle, and it's exciting kind of a spherically symmetric charge oscillation. It's kind of a dark mode. Optically, you can't excite it because polarization states of light generally don't allow for this. You'd have to come up with some kind of spherically symmetric polarization state to excite it optically. And then as you go through the center of the particle, you can again still see the surface plasmon resonance. I guess the height of this peak, I should mention, is about the same as the height of this peak because you're still passing through about the same amount of surface atoms. But the bulk resonance does become a bit stronger because now you have a lot more bulk sample that your electron is passing through. Okay, so what we can do is take particles. These were the same ones you saw a couple slides ago in the high resolution images, ranging from about 10 or 11 nanometers down to 1.7 nanometers, and look at the surface plasmon resonance. So exciting just on the edge of the particle. What is the plasmon resonance that you see? And here are the trends. You'll notice, first of all, that as you get to smaller particles, the signal-to-noise ratio does decrease. So as you're getting to smaller particles, you'll notice that there is a bit more noise, and also the line width is increasing. So that means that the plasmon lifetime is basically decreasing in such small particles. But probably one of the most notable trends is that there is a pretty significant blue shift in the surface plasmon resonance. And what we can do is look as a function of particle diameter as to what the peak energy is. So you'll notice that for particles on the order of 20 nanometers down to about 10 nanometers, even down to about 5 nanometers, the surface plasmon resonance stays roughly about constant, which is what you would expect using Mie theory. So it's only when you get up to larger particles that Mie theory starts to predict a pretty significant redshift for larger particles. So here, things are pretty constant. But then less than 5 nanometers, there is a pretty significant blue shift on the order of 0.5 electron volts. So this is a pretty huge blue shift for the surface plasmon resonance. It's basically going from about 3.4 EVs up to about 3.8 or 3.9 electron volts. We can also look at the bulk plasmon resonance. This also exhibits a pretty, significant blue shift. Here, though, smaller than the surface plasmon blue shift, so on the order of 0.1 electron volts. Okay, so how do we explain these peak shifts and also the peak broadening that we see in our spectra? Well, for a larger particle, if you just think about the surface plasmon resonance, here just kind of schematically shown bouncing around the particle, as you decrease the particle size, the conduction electrons are going to interact more with the surface of the particle, right? So they're going to scatter off of more surface states. There might be more defects. And that enhanced scattering basically can be classically accounted for using a damping term that's proportional to the Fermi velocity of electrons and also the radius of the particle. So this is basically a kind of a scattering frequency. A is just a constant. So if you include this damping term in the dielectric response of the particle or the optical response of the particle, that will give you the peak broadening that we experimentally see. So it basically means your plasmon is going to live for a lot less time due to surface scattering. But this would predict a redshift in noble metals. So if you look at silver or gold or platinum, if you were to just use this term and calculate the optical properties or plasmonic properties of noble metals, you predict a redshift. But we saw very clearly a blue shift. So how do we explain that blue shift? Our approach was to use kind of a quantum approach. So shown schematically here. If you take a bulk metal, generally you view the surface plasmon as a collective oscillation of the conduction electrons. But now, if you take the limit of that bulk particle becoming extremely small, say just 5 or 10 atoms across, then you know that for, say, a molecule composed of just a couple of atoms, you have discrete energy levels. In our particles that are 1.7 nanometers across, we have a few hundred conduction electrons, a few hundred atoms. So keep in mind that this is a slightly exaggerated picture. But we have basically a discrete density of electronic states where the energy levels are spaced very close together. And basically, electrons in these energy levels, when you excite a surface plasmon, are hopping from an occupied state below the Fermi level to an unoccupied state above the Fermi level. And if you work through basically what sort of plasmon resonance would emerge from accounting from all of these discrete electronic transitions, you find out that basically the frequency jumps of each of these transitions is blue shifted with respect to the classical plasma oscillation. And then because an electron can, say, undergo a jump from here to here, or from here to here, or here to here, there's a much broader frequency spread. So there's a little bit more uncertainty in kind of the plasmon resonance, and that leads to a broadening of the full width half max. So if we take this quantum model where basically we look at all the possible discrete electronic transitions that would be allowed in these small particles, even though those transitions are spaced by fractions of milli-electron volts. We sum over all possible transitions, and then we plot out what will happen to the plasmon resonance as a function of particle diameter. This is what we get, just assuming a simple spherical potential well. So we have a bunch of electrons in a spherical potential well. We get a pretty significant blue shift just using an analytic quantum model. And if we put our experimental data on top with no fitting parameters, other than accounting for the fact that our particles are on a substrate, the experimental data matches up quite nicely with this quantum analytic model. Note that it also shows quite a bit of deviation from just classical me theory, particularly when particles are smaller than 5 nanometers in diameter. So down to about 5 nanometers, there's pretty good agreement, I'd say, with me theory, at least within the error bars of our experiment. But below that, we're definitely not in a realm where classic me theory holds. We can also put in our data for the bulk resonance, and then this line corresponds to the calculated bulk resonance, so where the metal is becoming a dielectric. And again, our analytic model agrees quite nicely with the experimental data. Also, we can use a full ab initio approach. Here, basically, each of those electronic transitions was smooth in the ab initio code, which is why you don't see kind of the discreteness that you see in the analytic code. And again, the ab initio approach also predicts for smaller particles a pretty significant blue shift. And then you can extrapolate from an ab initio approach that only gets you out to about 3 or 4 nanometers how your dielectric constant would be modified for larger particles. And we get a very nice agreement between, again, this full DFT approach and our experimental data. Okay, so what is the takeaway message from this first part of my talk? Can we detect plasmons from particles in the sub-10 nanometer regime? The answer is definitely yes. But be aware that for particles of about 5 nanometers or smaller, localized plasmons become quantum confined. For those of you who work with semiconducting nanoparticles, you know that once you make particles small enough, basically excitons also can become quantum confined, and that leads to, say, a blue shift of the band gap that you'd get from a semiconducting particle compared with a larger semiconductor. So here we have something similar, except basically for collective oscillations of hundreds of electrons, we get quantum confinement around 5 nanometers. I guess, I don't know how many of you have taken a quantum class recently, but in a way it's kind of surprising that hundreds of electrons, when each electron is only moving on the order of a fraction of a nanometer, its de Broglie wavelength is very small, but overall this collective oscillation becomes quantum confined at 5 nanometers. So kind of a surprising result. Secondly, and probably most importantly for catalysis, something that we'll use when we start doing more catalytic reactions in the TEM, is that single electron transitions within these small metallic particles can significantly impact the collective response of a sea of electrons. So when we're in this regime where we're quantum confined, we can add just 1 electron or take away 1 electron, and that is going to significantly modify the plasmon resonances that we're working with. So anyway, just bear in mind, I think a lot of people kind of have the impression that plasmons and such small particles are so damped out that they're not really worth looking at. But I think there's actually a lot of really encouraging science that can be done, especially when they're in this quantum confined regime where we can detect potentially multi-electron redox reactions. Okay, so can we use these plasmons to monitor photocatalytic reactions in situ? Kind of one of my group's goals is to look at overall water splitting in the TEM using surface plasmon resonances. So just as a disclaimer, we're not there yet, but I'll show you some preliminary results we've done just in our optics lab to show that this sort of, I guess, photo-oxidation or photo-reduction process is possible. So a case study that motivated us was overall water splitting using dye-sensitized TiO2. So this was a cell introduced by Youngblood in JAX just a couple of years ago. And basically they have a ruthenium bipyridine dye that's responsible for absorbing the light. So basically this dye is sensitizing TiO2. So normally TiO2 just absorbs in the ultraviolet. This dye kind of extends the absorption range further out into the visible. Okay, so upon excitation in the green, basically you generate an electron hole pair and then the electron quickly transfers onto the titania, and then it'll kind of hop through or transport through the titanium to generally a platinum electrode that will be used to generate hydrogen from water. So we have water everywhere. Hydrogen gets generated over here at a platinum electrode. Okay, and then if you want overall water splitting to occur, if we have hydrogen evolution on the one hand, we need oxygen evolution on the other, and that comes from this iridium oxide nanoparticle. So basically an electron in this nanoparticle can basically regenerate the dye, and then in this case the whole gets used to form oxygen. So in my opinion, this was a really beautiful kind of dye-sensitized cell for overall water splitting. It turns out something that really limited the efficiency of this process was the slow recombination of the electron with the oxidized dye. So this process took about 2.2 milliseconds. And in contrast, this process, so the electron that we got from our dye into the TiO2, was much faster, on the order of 0.37 milliseconds. So the dye was more often regenerated from the electron that was already transferred to the TiO2, meaning that basically oxygen evolution was extremely inefficient. So I guess we're interested both in probing this process and in also coming up with a way of keeping the electron in the TiO2 for longer. So our way around that is basically to embed TiO2 with a metallic core. You can imagine maybe this is a nanowire that basically brings the electron to your platinum cathode. In these first experiments, we just started with a nanoparticle. So we have the silver core surrounded by a titania shell. The Fermi level of silver is just below the conduction band of TiO2. So upon illumination of TiO2, here in the ultraviolet, an electron will quickly transfer onto the silver. And then we can scavenge away the hole, basically with ethanol. So as you keep illuminating the nanoparticle, basically more and more electrons build up on the silver core. So this project started first by synthesizing well-dispersed silver core titania shell nanoparticles. And then we wanted to characterize their photocatalytic activity first in ensemble measurements and then in single particle measurements. I'll show you just the optical stuff now, but we'll get to the TEM hopefully soon. So we synthesize nanoparticles basically using hydrolysis of TTIP to coat on the silver core. This was a much more challenging process than I would have expected. Titania tends to want to form networks. So if you want to do single particle measurements using titania as a catalyst, it turns out to be pretty challenging just to get single particles to begin with that are coated with TiO2. But here in this TEM, you can see a number of individual metallic nanoparticles, each coated with a titania shell. And then if you just look at the absorption of the solution, for the silver particles, it peaks around 395. And then when you add the titania shell, we get a slight redshift because you've changed the index a little bit. And then you also get pretty significant blue absorption because the titania is now absorbing in the blue. Okay, so if we take our nanoparticle solution and we just illuminate it with a mercury neon lamp, here's our absorbance in the ensemble solution. So illuminated basically for 0 minutes, we get a nice surface plasmon resonance. As we keep illuminating it, we wind up blue shifting the resonance. That blue shift kind of saturates around 19 nanometers at about 5 minutes. So more electrons are being added onto the silver core. And then we can discharge it basically by opening up our solution to oxygen. And you'll notice that upon discharging, it takes a little bit longer, but ultimately the surface plasmon peak goes back to where it started. We also get a little bit more absorbance in the red due to like some trap states in the titania. Okay, so we get shifts due to charges collecting on the silver core in an ensemble measurement. What we want to do is basically do individual particle measurements. So we can also do this in an optical microscope where we put our particles in a flow cell where we have water and ethanol. And then in a dark field configuration, we just look at basically the scattering of individual particles upon illumination with ultraviolet light. So here's a dark field image. You can see a number of individual particles. Just zooming in to these 3. What we can do is in our flow cell, I guess, charge them up with ultraviolet light. So So you'll notice that each of these peaks now are at about 450 nanometers, so a little bit shifted from the ensemble measurement due to the effect of the substrate. And then as we charge them up, you get a blue shift of the resonance, and then you can discharge them, and you get a red shift of the resonance. So right now we're correlating these individual optical measurements with the electron microscopy kind of morphology of the particles. But you'll already notice quite a few differences between the ensemble measurements and the individual particle measurements. So here I'm just plotting the peak position of the plasmon resonance as a function of time, both during charging and discharging. And then here on individual particles, the peaks indicate the full width at half max of the surface plasmon resonance. So you'll notice, first of all, that the shift is quite a bit less on each of the individual particles than it was in the ensemble measurement. So it might be that we just didn't look at enough individual particles to see particles that had this big a shift, but already that's a pretty big difference. Secondly, the discharging dynamics are quite a bit different, or the charging and discharging dynamics. So here, it took very little time to charge up the particles. Here, it took quite a bit more time to charge up the particles. Also, these ones discharged quite a bit more quickly. So trying to unravel some of the kinetics of photocatalysis is what we're getting at. But already we see differences between particles and between individual particles and the ensemble measurement. Okay, so in the final part of my talk, I guess I wanted to address this question of whether we can improve below bandgap absorption of solar photons for photocatalysis and photovoltaics. So I guess many of you probably work in, I guess, solar research, so you know that kind of the quote Nate Lewis, the sun delivers more energy to the earth in an hour than humans consume in an entire year. So I think that's something that really motivated our group's research on solar energy. It's such an abundant source of energy. Unfortunately, of course, the sun spectrum is distributed across a broad electromagnetic range, with about 5% of the sun spectrum being in the ultraviolet, another 43% in the visible, and 52% in the infrared. And if you look at a typical solar cell, generally photons with energy less than the bandgap are going to be unused. So plotting basically the incident power as a function of cell bandgap. In blue, I'm plotting the power that actually goes to the cell. So you'll notice as the cell bandgap increases, the power decreases. This is why if you work through kind of a thermodynamic analysis, the optimal solar cell bandgap tends to be around 1.1 electron volts, where you're kind of ideally matching the cell bandgap to the solar spectrum. But I guess as your cell is absorbing less energy kind of above the bandgap, the amount of power transmitted is also increasing with respect to the amount of power that's available from the sun. So basically, we're putting to waste all the photons that have energies less than the bandgap of the solar cell. And we're also not efficiently using photons with energy just above the bandgap because of the low density of electronic states there. And also, most cells don't have 100% absorption above the bandgap. So as we reduce that above bandgap absorption, we're also throwing away more power. So in our group, we were interested in basically coming up with a way of better matching the sun spectrum to the cell. So our approach that we're considering is called upconversion. So the basic gist is that you take a solar cell, and then you have a thin insulating layer that basically electrically decouples the solar cell from the upconverter. So the upconverter is placed behind this insulator, and it can basically take two lower energy transmitted photons and combine them together to a higher energy photon that then can be reabsorbed by the cell above it. So most upconverters you can model as just simple three-level systems where you have two lower energy transitions kind of linked by some intermediate level, and then upon absorption of two lower energy photons, you get emission of a photon that is at or above the band gap of the cell above it. So I think probably one of the main advantages of upconversion compared to something like an intermediate bandgap solar cell or a multi-junction solar cell is that, first of all, you don't have to worry about additional recombination in the cell. So basically, because the upconverter is electrically isolated from the cell above it, you don't have to worry about current matching, you don't have to worry about adding in different defects, you don't have to worry about tunnel barriers. And that leads kind of nicely to the second point, which is that to a pretty large extent, you can separately optimize the cell above the upconverter and the upconverter itself, because you can basically work on each of these systems independently since you don't have that electrical coupling. Okay, so what is kind of the hope for upconversion, or the promise of upconversion in terms of impacting a solar cell efficiency? Well, here's a plot of cell efficiency as a function of cell band gap. And without an upconverter, like I mentioned, your ideal band gap is going to be at about 1.1 electron volts, where your cell absorbing media is kind of ideally matched with the solar spectrum in a simple thermodynamic analysis. If now you add in this upconverter, you notice that the efficiency goes from about 30% max at about 1.1 to 1.3 electron volts up to 44% max. And also the ideal cell band gap blue shifts from 1.1 electron volts to 1.8 electron volts. So it kind of brings your ideal cell from something more like silicon up to something more like amorphous silicon. So you kind of gain a little bit in that category where now the cell above your upconverter can be potentially a cheaper material or something that's more easily processable, like amorphous silicon or an organic photovoltaic. Lastly, I'd mentioned that solar concentration is not necessary to get a lot of bang for your buck in these upconverting materials. So here's a plot of the percent increase in efficiency as a function of cell band gap for different solar concentration ratios ranging from 1 up to about 1,000. And of course, the percent increase in efficiency is going to increase as you increase solar concentration. But that would be true for your cell anyway. So whether you have concentration or you don't need it to get a lot of bang for your buck by adding this upconverter behind the cell. Okay, so what is the impact of non-ideal upconversion on a solar cell? So the calculations I just showed you basically assume our upconverter is as efficient as possible. So it can take basically all of the incident photons on it and convert them to an above band gap photon. Well, here, let's consider a cell with a band gap of 1.7 electron volts, and we can look at the percent increase in efficiency as a function of the upconverter absorption efficiency, so how many photons it can absorb, and the upconverter recombination efficiency, so how many photons are radiatively emitted rather than being thermally lost. And you'll notice that you get the largest increases in efficiency when your upconverter absorbs a lot and when it radiatively recombines the most. So generally, we want to be up here in this sector of the graph where we basically have a high absorption and recombination efficiency in our upconverter. Also, if you look at the effective upconverter absorption bandwidth, most upconverters only absorb over narrow regions. So here, for example, is the thermodynamic limit, where we basically have no upconverter. And then as you increase the upconverting bandwidth, you get up to those calculations that I just showed you. So basically where you have the highest cell efficiencies for the largest absorption bandwidth. A few other design considerations. If you look at the AM1.5G spectrum, it has a number of absorption lines. So you don't want your upconverter to lie where you have any of those absorption lines, because that would result in a pretty small increase in short circuit current. And I guess here's where the ideal peak position for upconverter absorption would lie as a function of cell band gap. If we take a 1.7 EV solar cell, then the ideal upconverter absorption lines are going to be right around 811 nanometers and 1200 nanometers, assuming a full width half max of about 0.1 EVs for our upconverter absorption. So actually, this is kind of good news, because these are energy levels we can easily access with existing materials. Okay, so what are two promising upconversion systems? I've been told by the chairman I only have about 5 more minutes, so I'll go through this pretty quickly. One system that is actually quite efficient, on the order of 20% efficient, is a bimolecular system. So you can take like a palladium octaethyl porphyrin, combine it with a diphenyl anthracene. These two molecules undergo basically diffusional processes that allow for triplet energy transfer and triplet annihilation. And if you mix them together, you can take green light, in this case just from a handheld laser pointer. You can also do this with sunlight filtered in the green, because it doesn't rely on coherency of the photons, and you get blue light out. So here's the absorption in the green, the upconverted PL in the blue. If you don't have both of these molecules, if you just have this guy, basically this acts kind of like a phosphorescent molecule. So it has a triplet state, that's extremely long-lived. So just with PDOEP, if you illuminate in the green, you get red phosphorescence out. So this is a great system because it's already 20% efficient. It also can work in a polymer. So we've made large area polymers of these bimolecular systems. Another system that we're pretty enthusiastic about are the lanthanide-doped nanoparticles. So basically, this is systems such as like erbium and ytterbium that can be doped in a sodium yttrium fluoride matrix. These systems efficiently upconvert from 1550 or 980 nanometers into the visible, in the green or in the red, and you can really tune the pathways for upconversion. So you can get all of the light to be emitted in the green or all of it to be emitted in the red, depending upon what phase of nanoparticle you're working with and what lanthanides you're doping it with. So here's one example where a dye-sensitized lanthanide absorption here is peaked at about 980. I kind of cut off the 1550 nanometer line, but you can see the upconverted PL here in the green and also here in the red. Okay, so I'll just go through these calculations quickly, but when you look at the lanthanide systems and bimolecular systems, you can notice absolute percent increases in cell efficiencies that for the dye system are on the order of a few absolute percent if you have a higher cell band gap, so this would be pretty compelling for photocatalytic cells. For lanthanide systems, the percent increase in efficiency can exceed 10% for cell band gaps, kind of comparable to amorphous silicon. But really, you want to be operating in the regime where your upconversion efficiency is as high as humanly possible. And I'll just kind of put in a teaser here that for the lanthanide systems, as great as they seem for amorphous silicon, their efficiencies are more around like 1 or a few percent. So our group is developing, I guess, techniques by controlling both the local density of electronic states and the local density of optical states to enhance upconversion efficiencies in both of these systems so that way they can become technologically viable. And actually right now we have a collaboration with Bosch to incorporate some of our upconverting materials into their cells. So just as a quick Friday afternoon experiment towards enhanced upconversion, we basically made conducting upconverting composites where we combined nanowires with upconverting particles. Basically, without even trying, you can get almost a 4x enhancement in the upconversion intensity. But I do want to mention that nanowires are probably not the best system to use to enhance upconversion because you need the upconverter to be in the near field of the wire to really get the largest near field enhancements. Also with nanowires, you have a strong polarization and angle-dependent response. So instead, we're working with a system where we can basically consider something like a core shell particle, where the core is our upconverter, and then we have a shell around it that can both enhance the absorption of light onto the upconverter and then also enhance the density of state such that we get more emission back into the cell above it. So kind of the idea we have in mind is something almost like a metamaterial or a nanoparticle superlattice where we have an upconverter doped core. It's a silver shell, but it's a tapered silver shell. So it kind of looks more like a half moon shape or a crescent. In my talk, I don't have time to go into what motivated this design, but you can see here at least the results of some of our theoretical calculations showing that this design has a number of resonances throughout the visible and near-infrared spectrum, and these peaks can be designed to match with the absorption and emission of the upconverter. So if you look at just a near-field plot of the total enhancement in the upconverter doped core, it can be on the order of about 100. So you get really large field enhancements in the core, and also this structure has a pretty angle-independent response. So whether you're illuminating it at 45 degrees or 90 degrees, you still get a number of these resonances. I should mention here we're just plotting kind of the near-field spectra, so the distance from the tip. So here's the tip of our crescent structure, and then looking down into the core, what field enhancements are expected. Here's also a plot of the enhancement of the total upconverted power that gets radiated into the cell as a function of crescent orientation. And you'll notice we not only have a large absorption enhancement, but we also get an enhancement of the power into the cell that gets radiated back into it on the order of a couple hundred. So here's just a full field simulation of the solar cell with the upconverter behind it. Here you'll notice the upconverting kind of typical dipolar emission pattern without the nanocrescent, and then with the nanocrescent, at this particular frequency, you get an enhancement of about 100 of the power into the cell above it. Even though you're taking your upconverter, covering it with metal, because you're increasing the density of states, you get more power into the cell. Just one other quick response, because I think my 5 minutes are almost up. When you arrange these materials kind of in a lattice, you can also tune the index. So we have the ability to match the refractive index of this upconverting layer to the cell above it. Okay, so we can easily synthesize these nanostructures. We've most recently been using, I guess, kind of an angled evaporation, but we can also use colloidal techniques. We can make them over a large area. And then I showed you a number of resonances throughout the visible and near-infrared spectrum. In our theory, we see that in the ensemble absorption. We also see it in single particle measurements. And we can also do cathodoluminescence imaging spectroscopy to map out the different modes at each of these peaks. So here we're exciting with an electron and then detecting the light that gets emitted as a function of the electron position at 600 nanometers, 700 nanometers, 800 nanometers, and 900 nanometers. And I'll just show you in closing one quick movie, just looking at the light that's emitted from these crescents as a function of wavelength. So as we scan the wavelength, you can notice at shorter wavelengths, light's mostly emitted from the back. And then as we go to longer and longer wavelengths, you can see each of those resonances with kind of the beating of the light. And then at longer wavelengths, we're basically exciting a very efficient electric dipole across the tip. So you see a lot of light emission across the tips here. Okay, so coming soon. Again, I'd like to thank John for the invitation to come here. I feel like if we had like a few more months, we'd have results on upconverting crescents. But we've been making these bimolecular systems in basically small polymeric cores that will be the core of our crescent. We're also looking at lanthanide systems that are also spherical in shape and can be easily coated with these plasmonic crescents. So in summary, I guess I started off with these 3 questions. Can we detect plasmons from particles in the sub-10 nanometer regime with the hope ultimately of probing catalytic reactions in situ? The answer is definitely yes. Secondly, can we use these plasmons to monitor photocatalytic reactions? This is in progress, but I think the initial results are encouraging. And then can we improve below band gap absorption of solar photons? I'm pretty excited about the hope for upconversion to basically allow us to use some of these low energy transmitted photons. So I guess I'll end with this quote from George Bernard Shaw. Some see things as they are and ask why. Others dream things that never were and ask why not. So I'd like to say, in response to each of these questions, why not? I'd like to thank all of our funders who made the work possible, all of my group members who work very hard and also have a lot of fun, and thank all of you again for coming to this seminar. Hopefully you learned something, and I'm happy to answer any questions. Yeah. Yeah, that's a really good question. It's, I guess what you're basically doing is summing over all allowed quantum numbers for electrons in a spherical potential well. So you have a variety of N, L, and ML. And when you get to smaller particle sizes, I think there are certain kind of magic numbers where you wind up with basically filled shells or slightly unfilled shells. So right around 5 nanometers, you start to see kind of more discrete peaks in the analytic spectrum that just emerge from like what quantum numbers you're summing over and what specific values of N and L you have to work with. But we definitely don't see that when we use this ab initio technique where you kind of smooth over all of the transitions. And I think based on like surface stamping effects, probably experimentally resolving each of those discrete peaks would be very, very challenging.
In the second part of your talk, you showed one slide, I think we're using ethanol as a sacrificial electron donor.
That's right.
And was it silver coated with titanium dioxide?
Yep, that's right.
Is the implication or a measurement showing that you are generating hydrogen in that system somewhere?
Oh, we're not generating it here, but you easily could. So for example, if you had the electron in silver and just transported that say, two hydrogen evolving catalysts, you could do that, but we're not doing that here. Basically, we're just storing the electrons now on the silver and then discharging them through the titanium once we introduce oxygen. So we're not evolving hydrogen, but
I'm a little puzzled by the net chemistry that's going on.
Yeah.
You're doing real chemistry on ethanol.
That's right, that's right. And then the electrons are just being stored in the particle. The particle has a capacitance, like it can basically hold onto a few hundred, potentially a few thousand electrons without exploding.
Okay, but they have to go somewhere if you're going to have a product like...
Oh, that's right, that's right. So this system, we don't have that, but we ultimately will. So the kind of the ideal geometry would be something where you have a nanowire, say, coated with titania, and that nanowire ends at a hydrogen evolving catalyst. And then you functionalize, say, the titania with an iridium dioxide particle or some oxygen evolving catalyst. So you're absolutely right. Ultimately, you want that to go someplace, but as just kind of a first step along the way, we just want to know, can we probe charge transfer processes?
Well, you're still going to be faced with the nasty oxygen problem.
No, of course, yeah. Yeah.
Presumably, if you just disperse that with platinum on the surface, you would evolve hydrogen.
That's right, that's right.
Pretty common. The question is, have you considered putting the iridium on the surface of the anatase for the oxygen evolution reaction and circumvent this whole ruthenium complex thing?
Yeah, no, that's also definitely kind of like a next step. Like, I guess my lab is more of a nanophotonics plasmonics lab, so we want to know, can we use plasmon resonances to detect electron charge transfer? And if we can, then the goal is to do that on an actually useful system. Like, I make no claims that what we're looking at is useful, but it's a good baby step. So you're absolutely correct. Like, if ultimately you can have a hydrogen evolving catalyst and then, say, the iridium on the TiO2, and then can we use, say, these plasmon resonances to probe these multi-electron redox reactions in real time to figure out what's happening during the full water splitting reaction?
People talk a lot about these very finely dispersed nano-catalysts on the surface of the substrate.
Right.
Photochemistry and electrochemistry. One of the technical issues is when you get down to very, very small particles, you do get migration on the surface.
That's right.
These particles can coagulate, if you like, and so you have to have potential energy wells for these things to
Exactly.
be anchored to.
That's right, that's right.
Presumably this technique would allow you to monitor the stability of these.
Exactly. And here, everything was done for now in the optical microscope, but that's why we're so excited about in situ transmission electron microscopy, because right now we've built the liquid cell, we can do the imaging, we can do the plasmon resonant detection, and the hope is really to be able to follow not so much with ultra-fast time resolution, but at least with millisecond time resolution, what's happening to the electrons and what's happening to the particles in terms of how they're migrating and what's the best surface morphology, what's the impact of the substrate on catalysis. So yeah, I totally agree. These are really important questions, and figuring out what's happening during the reaction is kind of what drives our scientific curiosity.
Your photocatalysis system showed a similar Fermi level that's in between your valence band and conduction band of the titanium oxide. Can you explain why the electrons would like to go from titanium oxide to silver? Because it will form a Schottky pattern when it comes in contact. That band diagram is correct when they are separate, but when you're having them in contact, because the Fermi level of silver.
Right. Yeah, so your Fermi levels are going to equilibrate. You do have a bit of a Schottky barrier, but
And why would the electrons then go from titanium oxide to silver? Why would it like that go from? Because it's already, the silver is already charged with electrons when they come in contact. So I don't understand particularly.
Okay, well, I'd say your silver particle is still neutral. You're charging it up upon UV irradiation. So you have, I guess, we're exciting above the band gap of titania. So we're exciting at like 300 nanometers. So the electrons have enough energy to like easily transfer onto. Yeah. So we're pretty high above the conduction band of titanium when we're exciting.
No, actually, can I
Yeah.
answer both your questions? First of all, yes, you will have a Schottky barrier, and so there will be a charge transfer from the silver to the titanium oxide even before you irradiate, and there will be a Schottky barrier to overcome. But your UV will have enough energy
That's right.
to overcome that barrier, and so you would then load up even more electrons.
That's right. Yeah.
When you irradiate.
That's right. So we're assuming we're in equilibrium when we start. We're in the dark, and then when we illuminate, we're at 305 nanometers or so. So it's a pretty high energy compared to the band gap.
However, having said that, the position of your plasmon in the core shell particle should already be shifted from what you would calculate if you assume bulk dielectric constant for the TiO2 because of the shock heat.
That's right. That's right. That's right.
And probably there is.
Yeah, and that's indeed the case. Yeah. I think, I can't remember the exact numbers. Was it like 420 or so? Yeah, slightly blue shifted in experiments compared to what you'd get if you just assumed a shell that has a 10 nanometer thickness and a core that's 10 or 20 nanometers in diameter. So that's, yeah, absolutely correct, because you've got a slightly higher electron concentration.
Which only proves that although we don't know how to solve Schrodinger's equations, the electrons do know how to solve them.
Exactly. They're smart electrons.
So I think we have another question.
So you said a lot of people use the ligands, and that's a problem, but they use it for a reason. I'm wondering how you got around that.
Yeah, yeah. So I guess I said we don't use organic ligands. So a lot of people use things like oleolamine or like citrate, where you have a lot of carbon, kind of long, bulky carbon chains. We get around that using borohydride, which basically serves as kind of an electrostatic stabilizer in solution and prevents aggregation when you disperse it on a substrate. But we do have our particles on a conducting substrate, so that charge is dissipated very quickly once it's on a substrate. So basically, we're using borohydrate as both the reducing agent and kind of an electrostatic stabilizer in solution. But our particles, because we're kind of playing around with these charging tricks in solution, are not long stable over like long periods of time. So what we're doing when we want to look at now catalysis, say in palladium nanoparticles, is we can use a conventional organic ligand-based synthesis, but then do either a ligand exchange or get rid of the ligands with, say, like other techniques. For example, just throwing out a couple, like a UV, like ozone or like a plasma clean before you do the TEM measurements. For us, since we're interested in situ TEM, long carbon chains would just be a killer for any measurement because you'll just deposit soot everywhere.
Okay, well, let's thank Jen.
Oh,
I
you're
love
so
the
sweet.
particles. I want to say I love those particles. The fact that you load them up with electrons and use them later. I mean, you could probably turn that into a strength rather than because you're basically storing.
Right.
So if
exactly.
you could do it in some way that you